chapter 14, and last time before the exam there, we started talking about weak acids. And again, when we want sort of the pH of weak acids, because they are weak, they obviously will set up an equilibrium, which means you do need to do an ice table. And really, the ice table is the same as all the other ice tables that we've done. The only difference is when you have sort of a weak acid, say like HF, you go through your ice table. Obviously, when you get down here, that's going to be probably 0 plus X plus X. And obviously, you'll have a molarity here minus X. And when you get down here, you do solve for X. X will usually equal the H plus concentration, which means you can then go into your pH equation at that point to solve for the pH of it. You could solve it any way that we've solved it before, quadratic assumption. Again, you usually will probably not hit too many perfect squares or anything like that on these. So those are probably your two most common ways. I think the last one we did, you needed to make sure you check the assumption as we talked about. Again, it's not always going to work. Any questions on that there? All right, so I don't remember which one we were. Did we do this one? Whoops. Did we do this one? I don't think we did, right? No. Oh. I think we did the one before it. That one we did, I think. So let's do this one here. What is the H plus concentration and the pH? Why not as well? For a 0.01 molar HCN solution, Ka value there 6.2 times 10 to the minus. Okay, let's take a look. So once again, a couple of things we talked about. We hope we know that's an acid. We know that it is a weak acid because we do have obviously a Ka given to us. So definitely an ice table would be the approach here. We would take our weak acid and we would break it apart into H plus and Cn minus in this case. That would give us a Ka sort of expression here of H plus times Cn minus divided by HCN, and that's going to equal 6.2 times 10 to the minus 10. Going initially here, 0.0100, change minus X plus X plus X here, coming out 0.01 minus X, X, and X. So again, sort of a basic table. Just like normal, we're going to take everything here and basically put it into our expression up on top. That's going to give us X squared divided by 0.01 minus X will equal 6.2 times 10 to the minus 10. At this point, we could definitely assume that X is equal to 0 and give it a try. Remember, we're just going to get rid of the 0. We're subtracting or adding to a number. That's going to give us X squared divided by 0.01 equals 6.2 times 10 to the minus 10. Again, we're going to first multiply that to the other side, and then we're going to square root it. So if we do that, that's going to get us here. Too many zeros right at this hour. It's going to give me an X value here of 2.4899 times 10 to the minus 6. We do want to check it, so we'll divide that by 0.01 and times it by 100, and our check should be good here. I don't even think it's 0.1%, so we should be pretty darn good, I think. So it's like 0.02%. All right, so that X would be then, with a little bit of rounding there, our H plus concentration here. As obviously, if we go to our table, we can see that is what the H plus equals. Looks like number 2. Since we're also looking for a little pH action here, we could then go into our pH. We'll use the rounded number here and see what we get. About 5.6 pH, which is acidic, so that's good as well. Any questions on that? Again, you could always quadratic if you like to without doing the assumption, but might as well give the assumption a go, I would think, yeah. Any questions on that there? So let's then talk about percent ionization. So percent ionization, good talk. Let's go back and talk a little longer. Percent ionization is the ionized acid concentration at equilibrium divided by the initial acid concentration times 100%. The calculation for percent ionization is essentially the calculation that we do to check our assumption. That is the H plus concentration divided by the initial concentration of the acid times 100%. So actually the check that we do when we make the assumption is actually the percent ionization. And if it's considered 5% or less, as we've been doing, it's considered not a big change or significant amount of change that occurs. Percent ionization is, or percent dissociation is how much a acid or even a base, you could do it with as well, breaks apart in solution and produces ions. And we have something that is a strong acid, has, as you can see here, 100% ionization. It's just going to completely break apart. We do see a different amount of percent ionization here when we look at a weak acid. And as we saw before, and we talked a little bit about last time or time before, that our assumptions sometimes will work and will not work, really based on the concentration of the acid to begin with. And that's really what we see here. When we look at a much higher concentration, we have a much lower percent ionization. And again, when we have a smaller concentration, we have a much higher percent ionization. So when we talked about sort of that, like that pizza example, again, if you had a whole pizza, which would put you over here, you just take out a slice, it's not going to be as much of a loss to your overall amount that you started with. But if you started again with just a couple of slices there of pizza, you take one, that's like 50%. That's a much greater percent that you lost. And that's why, again, in times when we have a smaller concentration to start with, like we saw in that example where we had 0.5, the assumption worked, but when we went to 0.05, the assumption did not work. Again, the amount that's lost is significant to where you started from. So if you have a larger concentration, then if you lose a little, it's not as significant as if you had a very small concentration to begin with and you lose a little, that is significant. That is also, by the way, when we do, assume x is equal to 0, besides the fact that, when we have just the x's, like plus x, for example, we started with 0. Anything from 0 would be significant because it started at 0, which is nothing. So anything that you make is relatively significant, besides the fact you can't solve for anything at that point. But that's why we don't get rid of, obviously, all the x's along the way. So you can plug this in to solve for the percent ionization. Again, you got initial concentration of the acid on the bottom and how much H plus you have basically come off. So we could actually use this type of information in another way. We could use it to help us calculate something. For example, like in this example here, where we're actually looking for the Ka of formic acid. We're starting with 8 molar formic acid. It is 0.4% ionized. So if we were to sort of approach this like a normal sort of weak acid problem and set up our equilibrium here, and we know it's a weak acid because obviously we're looking for a Ka value. We would have our Ka in this case would be our H plus and our HCOO minus and our formic acid. That equals not sure because that's what we're looking for in this particular case. So initially what we do know though is we do have 8 molar of this acid to start with. We have none of this guy. Change will be kind of like normal, minus x plus x here. That means at equilibrium, 8 minus x, and x. So a normal sort of ice table we could kind of take here. Like normal, we normally would actually put it into here and solve for x, but in this case, we don't know what the Ka value is. So we want to think about maybe the other piece of information that was given to us, which is that this acid is 0.4% 0.47% ionized. And we take our percent ionization sort of formula, which is the H plus concentration divided by the initial concentration of the acid times 100%. We know that it is 0.4% ionized. We know the initial concentration of the acid, which was 8 molar. That would allow us to solve for H plus in this case. And the reason why solving for H plus, which would then equal the percent ionization times the concentration divided by 100%. The reason that would be very helpful for us is if we could figure out our H plus concentration, we could see from the table that that is what X equals at equilibrium. So it's very similar to the experiment you're going to do today. You can kind of back calculate a little bit here, our K value. So putting in our numbers here, we have our not 8%, we have our 0.47% times our initial concentration, which is 8, divided by 100% here. That's going to give us our H plus concentration, and in this case, that will get us 0.0376 in this case. So now that we figured out the H plus concentration, that is 0.0376. That is also what X equals, which means this guy's concentration at equilibrium would be 0.0376. And this guy's concentration would be 8 minus 0.0376. And if we do that, 8 minus 0.0376, we now have 7.9624. We now have 3 values at equilibrium that we can now put into our expression and actually get the value of Ka. So in this case, our value of Ka would be 0.0376, and that would be squared up on top, divided by our 7.9624. And that's going to get us here about 1.8 times 10 to the minus 4 would be our Ka value in this case. So this is obviously another way that you could use something like percent ionization to help you calculate. Again, using that to figure out really your H plus concentration at equilibrium. And you can back calculate everybody else's concentration to get to the Ka value. Clearly as well, you could just go right into the percent ionization sort of formula to calculate, the percent ionization if you have that information. Any questions on that there? Yeah. And like I said, you can also sort of apply this to a weak base or a base as well. So speaking of weak bases, let's talk a little bit about what happens when we deal with weak bases. So much like weak acids, a weak base will set up an equilibrium. And again, unlike acids, I would recommend writing water into formula for anything that is a weak base, so you can kind of visualize what's happening, which is we're sending the H plus over there. That's going to set up our equilibrium here, and NH3 is definitely a weak base. And it will give us NH4 plus and OH minus. This is going to give us our products over our reactants, and this is what is known as a Kb to add to our ever-growing list of K values. Kc, Kp, Kw, Ka, Kb now. And here, Kb is the ionization constant for weak bases. Much like a weak acid, weak bases are the only type of bases that have an equilibrium constant because, again, if it is a strong base, much like a strong acid, it's going to completely break apart. It's not going to be a reversible type of situation. So once again, if you do see a Kb value, you will know that what you're dealing with is a weak base. Now, when we do these things and we look at a Kb value, as the Kb value increases, the strength of the weak base also increases for really the same reasons we talked about with the acid, which is if I have a large value of K, that means mainly products. And if I have mainly products, that means I have produced more hydroxide. And that's really what makes something a base, is that ability, right, to produce free hydroxide in solution. So with a higher Kb value would mean you would actually have more free hydroxide in that solution, making it a stronger weak base. Again, it is nowhere near as strong as a actual strong base like sodium hydroxide, potassium hydroxide, and those things. But it will, in comparison to other weak bases, the larger the Kb value, the stronger the base is. Now, how do we go about doing these problems? Well, as you might imagine, we would do like an ice table type situation happening. And the one difference that you do need to remember when you're doing this type of table is, for example, you'll have some molarity, some zeros. You'll have minus x's, plus x's here. You'll have your initial minus x, x, and x. When you do solve for x in this case, you do need to remember that it is not the H plus concentration. It is actually the OH minus concentration. So in this case, you do got to probably go the POH route first and then subtract 14 to get you to the pH. So again, sometimes people at this point, when they solve for x, they just automatically think, okay, just go right into the pH equation, and that's the H plus. But again, this will be the OH minus in this case. Any questions on that there? All right, so why don't we take a look at some values here. And again, in your table, you can be asked to look up some values. I would say probably your most common weak base is ammonia, but a lot of organic guys that have nitrogen and so forth in there, which are sort of ammonia based, are a lot of where the weak bases come from. So why don't you give it a try here. We have an amine compound, has a Kb of 5.6 times 10 to the minus 4. What is the pH of a 0.15 molar solution of this weak base? Okay, so let's take a look. So a couple things, right? Obviously, we have a Kb, so we know this is a weak base. So we do need to do an ice table. So we'll start with the equation. And again, like I said, more so than probably the acids, it's probably a good idea to include the water with your reaction here with a base. So again, you can maybe just visualize the H plus coming off and where the hydroxide comes from in this case, and that would give us basically just the same thing here, but add a H plus to it. And that is, again, how we're going to generate the hydroxide from the water. So definitely probably a good idea to include it here in the reaction. Initially, we got 0.15, we got 0 and 0. We got our minus x, plus x, and plus x. That means here at equilibrium, 0.15 minus x and x and x. Any questions on the table here? It's going to give us a Kb of our products here over our reactants. That's going to equal our 5.6 times 10 to the minus 4. You could then put your stuff in there, and that will get you x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. You could assume x is equal to 0, and if you checked it, it is a bad one, so no good on that one. Here it's like 6.11%, I think, which is not so good. So we do need to quadratic this one. So we're going to multiply that to the other side. That's going to give us x squared is equal to with a lot of zeros, 1, 2, 3, 4 zeros there, minus 5.6 times 10 to minus 4x. Bringing everybody to the same side should give me x squared plus 5.6 times 10 to the minus 4x minus 0.000084. That's going to go into our quadratic here. So our x would equal minus 5.6 times 10 to the minus 4, plus or minus, if we clear up what's inside, 5.6 to the minus 4 squared, minus 4 times a, which is 1, times c, which is negative 0.000084. It's going to get you something like, I think, 0.00003363-ish inside the square root. And then if you square root it, you're going to get something like 0.01833, we'll call it, or maybe 4, which we're around the 4. All divided by 2 times 1, which should be 2 in that case. That obviously, like normal, is going to give us a couple of values there for x. We'll do the adding first. So negative 5.6 to the minus 4 plus 0.01834 divided by 2. Going to give us an x value here of 0.00889 r. We go r minus, which probably is not going to be great here since it's going to give us a negative number. Will get us a negative 0.00945. Obviously, this one is not going to be good as the hydroxide is equal to x, and we can't have a negative concentration. So this then should be our hydroxide concentration. And again, it's important to remember that it is the hydroxide concentration in this case. Whoops, come back. And that means we could actually go into our, I'll do up here, POH equals negative log of 0.00889. So minus the log 0.00889, and you get something like 2.05. Now, if you for some reason thought that that was the pH, it should not make sense to you, right? Because that definitely is not a basic pH, if you for some reason thought that. Here we then want to subtract our 14 here to get to our pH. So 14 minus our 2.05. Going to give us a much better pH here of 1195. Looks like a winner there. That is definitely basic, which would match the fact that this is a base, right? Any questions on that there? So again, also another good reminder, make sure you do check your assumptions. May not always work. Yeah. Any questions on any of that there? So very similar to weak acids, except here at the end we do get hydroxide. So usually one additional step that you have to do POH and then to the pH. All right. All right. So we talked about a second ago our weak acids, which has a Ka sort of expression. We have our Kb for our weak bases. And if we were to add a Ka reaction, a weak acid with a Kb, a weak base type of situation, what will happen in this case actually is we'll start crossing things out. And what we're actually left with is water, basically. And that it also has a K value, which is Kw. And remember that when we add equations together in terms of the K values, we multiply them. And that gives us a really important sort of relationship that the Ka times the Kb value will actually equal our Kw. That Kw is the same Kw we use in the calculations. 1 times 10 to the minus 14 is Kw, right? So this is a really good way. In some cases, you may be given the wrong K value. So what I mean by that is in a problem, you may be given the Ka value, but you actually need the Kb value, and vice versa. You may be given the Kb value, and you actually need a Ka value. So you can actually use this to convert between the two. Again, using 1 times 10 to the minus 14 for Kw to do so. Now, the other important thing to remember and to always think about is which K value should I use in a situation? And this is why being able to write equations is really important in this class, because if you see on your product side, you have H plus are H3O plus. That's an acidic situation, and you definitely should be using a Ka value. If you write your equation correctly and you look on the product side and you see hydroxide, that is a key that you're dealing with something that's a base, and you should be using Kb. So again, being able to write these equations correctly will lead you down in terms of the calculation, hopefully correctly as well. So if you see OH minus on the product side, you should be, if you're doing a calculation, be using a Kb. If you see H plus or H3O plus on the product side, you should be, again, using a Ka value in those calculations. And again, that's the importance of being able to write those equations, because I've seen people write for a base, they end up with H3O plus, and obviously that affects the calculation and everything along the way. Any questions on that? Let's then talk a little about acid strength. And there's two types of acids, really. There is acids that have oxygen and really acids that don't have oxygen. And when we look at acids that actually do not have oxygen, one of the things that you might think that you want to look at is electronegativity. And when we look at an acid that doesn't have oxygen, like HCl, HBr, whatever it may be, is obviously this bond here that we need to break, right, to release that hydrogen out to make it basically an acid. But we actually don't look at electronegativity when we're trying to compare acids that don't have oxygen and see which one's stronger. We actually look at bond strength or bond enthalpy. Perhaps you might remember that when you talked maybe about bonding, and you have to add up all the bonds you broke and all the bonds you made, and it was a double bond, a triple bond, a single bond. It has different values. So bond energy or bond enthalpy is actually the sort of consideration that we look at when comparing acids that do not have oxygen. The stronger the bond enthalpy, the weaker the acid will be. So for example, when we look at HF versus HCl, HF has a much higher bond enthalpy than HCl, which means in comparison, it's going to take a lot more energy to break this bond for HF than it would to break this bond for HCl. That means the HCl bond will actually break easier, less energy, and come off a lot easier than HF's hydrogen. And because of that, the HF will actually hang on to its hydrogen a little bit stronger, and it will actually be a weaker acid because it's not releasing the hydrogen into the solution to make it an acid, basically, in that case. And that is why, actually, if you look at HI is actually a stronger acid than HCl. Never gets a lot of contention. Or HBr is actually a stronger acid than HCl as well, because it has a weaker bond energy. So HI, you just look at it and it will pop off that hydrogen. It doesn't take a lot of energy to release it, and makes it a much stronger acid. So in terms of group 7, where we find most of our acids that do not have oxygen in it, bond strength increases as you go up, and that means acid strength increases as you go down, with HI being the strongest acid. HF is a much weaker acid. Any questions on that there? Here's a table from your book here, same idea. Again, as you go down, we see increased acid strength, and as you go to the right on the periodic table as well, increased acid strength. And an opposite relationship, right? So if I have increasing acid strength coming this way, we would have increasing base strength going that way, opposite relationship of what we have going on. Now, when we do have oxygen in acids and we want to compare sort of acid strength, these are what are sometimes referred to as oxyacids because they have oxygen in them. And most oxyacids have pretty much this bond here, that OH bond, and it's that OH bond that gets broken, and that is the hydrogen that basically comes off and makes it an acid. Like if you looked at something like nitric acid, looks something like this. And it's this right here, that OH bond that basically comes off or breaks off and allows that hydrogen to be released. So when we're dealing with oxyacids, there's actually two things that we look at, and depending on the situation, you may look at electronegativity And a reminder on the periodic table, electronegativity increases as you go up and to the right, and fluorine is the most electronegative, right? So increases this way on the periodic table with fluorine being the most, and decreases as you go down. The other thing that you could look at is the oxidation state. And you might remember that maybe when we talked a little bit about redox reactions and calculating oxidation states. So in certain situations, you look at electronegativity. In other situations, you would look at the oxidation state of the central atom. So if we take these two acids here, and if we look at these oxyacids, and they have different central atoms, but they are actually from the same group, they actually will end up with basically the same oxidation number. So just a reminder how to assign oxidation numbers. If you have oxygen, that's a great place to start. That's a -2, a -2, a -2. Hydrogen is +1. So if we add all that up, that's a -6, and +1 is a -5. To balance it out to 0, the bromine here is using a +5 oxidation state. Same thing, we come over here, -2, -2, -2 is the oxidation state of oxygen, +1, and same idea, that's -6, and +1 is -5. That means the chlorine here is also has an oxidation state of +5. Reminder that the oxidation state is not the charge, it is what is actually sort of its charge in terms of what it is bonded to and electronegativity differences. And so, as you know, chlorine and bromine in an ionic compound is -1 charge, but actually in a covalently bonded one where they're sharing electrons, actually it has a more positive sort of charge that's happening. Now, because they both have the same oxidation number, you cannot use oxidation number to determine which one is a stronger acid. In this case, what we would look at is actually electronegativity. So when we look at electronegativity, chlorine is more electronegative than bromine. So if you remember, this bond right here is already a polar bond, right? Oxygen is more electronegative. Electrons are being shared unequally in this case. And because chlorine is more electronegative, it's going to pull those electrons closer to the chlorine. And what that's going to do is weaken this bond and allow this hydrogen to come off a lot easier. Same idea here. This guy is going to be more positive, this guy is going to be more negative. But in comparison to chlorine, bromine is less electronegative. So it's not going to pull as much of those electrons in and not weaken that OH bond as much. And less of it will come off. It still will pop off, but less of it will come off. So based on electronegativity, the HClO3, the chloric acid, is actually a stronger acid than the bromic acid there in this case. Any questions on that? So if you have a central atom, same oxidation number, usually that means they pretty much have the same stuff attached on the outside. You want to look at electronegativity. The one that is more electronegative is a stronger acid. Now, if you have a different situation where you actually have the same central atom, and in this case, all these guys have the same central atom, which is chlorine, that means obviously they all share the same electronegativity because they're all chlorine. We actually do need to look at oxidation number here. And again, if we were to assign our oxidation number, this would be -2 +1. That gives me a -1. So the chlorine here is taking on a +1 sort of oxidation state. That is -2, -2, and +1 gives us a -4, and 1 is a -3. Going to take on a +3 for that chlorine. Once again, the one we just did, -2, -2, -2, and +1. Going to give us a -5 overall, taking on a +5. And lastly here, -2, -2, -2, and -2, +1 for the hydrogen. That's a -8 + 1 is a -7. The chlorine here going to take on a +7 in this case. Again, you could hopefully see here, and we'll talk more about it when we get to the redox chapter, to remind everybody, but again, chlorine normally thought of as having a -1 charge, and that is true in an ionic compound. But here, when they start to share electrons, based on who it is sharing electrons with, we do get a difference in electronegativity here, and it actually takes on a much more positive charge in this case because there's a lot more oxygens happening here and making it more and more electron deficient as the oxygen is more electronegative. So in this case, our strongest acid would be this guy right here, perchloric acid. Again, with that big old +7 charge or oxidation state, it's going to pull those electrons in a lot closer. It's going to weaken this bond a lot more than the +1 pull of the chlorine here. As you might remember, when we talk about sort of positive and negative attraction, the strength of that attraction increases with the size of it. So something that's like a +7 is going to pull things closer to it than something like a +1. It's not going to pull them as close. So in terms of strongest acid, that would be the strongest. That would be the next strongest. This would be the next one, and that would be the weakest out of the bunch in this particular case. Any questions on that there? All right, then we're going to talk about then salts next. And salts, obviously, as you may know, basically originate from the reaction, right, of an acid plus a base will basically make a salt and water, right? That is your classic acid-base reaction. A salt's an ionic compound. And when we talk about a salt, there are certain salts that when they are produced can continue to react with water and actually affect the pH. And at some points, these two guys can continue to react and affect the pH by either producing H3O plus or OH minus. So that would make it either an acidic solution or a basic solution because the formation of the salt will continue to react. Now, an important relationship that we talked about earlier on was that if you have an acid and its conjugate base, and if it has a strong acid, its conjugate base will be relatively weak. And if it has a weak acid, its conjugate base will be relatively strong. Same thing with our base and its conjugate acid. If you have, again, a strong base, its conjugate acid will be relatively weak. And if you have a weak base, its conjugate acid will be relatively strong. So if a salt conjugate base or conjugate acid comes from a weak acid or, I'm sorry, from a strong acid or a strong base, it'll be relatively weak, which means that salt, when it goes to try to react with water, will not happen. And you'll basically get kind of no additional reaction, no additional production of H3O plus or not. You can have a salt that can react with water. And in a case, the salt may accept the H plus. The result of that is you will produce hydroxide and that solution will be basic. You could also have a salt that will actually donate an H plus over and act as an acid. The result of that is you can produce H3O plus. If you do this, you would expect the solution to be basic. And if you do this, you expect it to be acidic. If it does this, it's basically going to be neutral. You're not going to get anything happening. pH there is going to be basically 7 of that salt solution. Any questions on that there? Yeah. So let's take a look at some of these here. So if you have a neutral solution of a salt, that is usually something that comes from group 1 or group 2 on the periodic table. And if you remember, group 1 and group 2 on the periodic table is basically where we find our strong bases. And so those guys are going to be basically neutral salts. So for example, sodium. Anything that comes from sodium hydroxide is going to be neutral. Also, anything that comes from a strong acid will also be neutral as well. So for example, if you had sodium chloride and you're not really sure maybe what it came from, what you might want to think about is what two things, an acid and a base, could make sodium chloride. Hopefully you can reason that if you took some hydrochloric acid and you took a little sodium hydroxide action there, you will get water and you will produce sodium chloride, which means most likely this salt came from hydrochloric acid, which is a strong acid. That means the Cl minus that came from the strong acid is going to be neutral. It's basically not going to continue on and do any type of hydrolysis reaction, which is the reaction with water. If you think about the sodium, it most likely came from sodium hydroxide, which is group 1 and a strong base, also not going to go through hydrolysis and react with water. And that's basically what these reactions are. These reactions are sometimes referred to as a hydrolysis reaction because basically it involves water basically reacting in this particular case. Now, that's not the case, though, if we look at, say, something like sodium acetate. So if we took a salt like sodium acetate here, sodium acetate is a salt, and because it's a salt, it's an ionic compound. It's also a strong electrolyte. And what's going to happen in this case is the sodium acetate would break apart into a sodium ion and an acetate ion. And usually when you're dealing with a salt solution, that's really what you kind of want to think about is what are the ions this salt breaks apart into? And secondly, will any of those ions react with water and go through this hydrolysis sort of reaction? So what we want to think about is, again, maybe where that salt could have originally came from. So since it's sodium acetate, I'm going to assume that acetate sounds a lot like acetic acid is probably where that came from. And probably sodium hydroxide here. And again, in this reaction, we would produce our sodium acetate. And again, we will produce our water in this case. Now, obviously here, our sodium hydroxide is a strong base. Acetic acid is what type of acid? Strong or weak? It is weak. And by the way, you know that by the process of elimination of the 6 strong acids. It's not one of the 6 strong acids, which means it's probably a pretty good idea. It's going to be weak in this case. So we already know earlier that sodium from above definitely came from probably this guy and it's group 1, which means it's basically going to be neutral, right? So that's going to be neutral. We don't have to worry about it. But when we look at acetate, acetate came from this guy, which is a weak acid, which means acetate here will be relatively strong in the sense that it will actually continue to react with water in this case. Now, if it did come from this weak acid, that would mean that the acetate is actually like its conjugate base. And that's an important thing to remember because when the acetate decides to then react with water, it's going to react with water as a base. And a Bronsted base is somebody that will accept the H plus. So it's going to actually accept the H plus in this case. Again, by thinking about where it came from, I know it's going to be a base. And again, that's going to allow me to know that it should accept the H plus. The importance of that is you will actually make always in the situation. So if you're not sure what you make, this is what you always make. You always make where that salt came from. So this came from acetic acid. When it reacts with water, you will actually always make back where it actually came from, which is a really good thing because a lot of times in the problem, they'll actually give you some information about acetic acid. So you'll usually have the actual formula there for you. More importantly, though, this thing is going to produce hydroxide when that water gives away its H plus. That production of hydroxide should tell me a couple of things. First thing it should tell me is if I were to calculate the pH here, it should be acidic, basic, or neutral. Should be basic, yeah, because we are producing hydroxide. Also should tell me, by the way, if I'm doing a calculation, what type of K value should I use? KB. And I say that because a minute ago I said sometimes there's problems where they'll give you the wrong K value. These are the problems: salt problems, hydrolysis problems. You will most likely have in this problem the Ka value for acetic acid. And you would not want to use the Ka value in this case because it is basic, it is producing hydroxide. That is where you could use what we saw earlier, our Kw equals our Ka times our Kb, and you could get your Kb value that you want to use. The other important thing is you would solve this like a regular ice table, right? Some molarities, some zeros, some minus x's, plus x's, molarity minus x, x, and x. Obviously, go in there and solve for x. A reminder again that x in this case is the hydroxide concentration. So you probably got to go POH first and then the pH. So again, writing these equations really, really important. Otherwise, if you write H plus there, you're definitely doing the wrong calculation. Even if you get the equation right, understanding what it means is also important because people just automatically throw the Ka value in there because that's what's given to them. They figure that's what I should use. So you got to really think about what's going on here. And again, this should end up as a basic salt solution because of the production of hydroxide caused by the salt that's there. Any questions on that there? All right. Now, in addition to obviously neutral salts and basic salts, we can definitely have an acidic salt as well. And this salt, for example, here, ammonium chloride is an example of that. And if you think about perhaps where ammonium chloride would come from, maybe you would think about a reaction of hydrochloric acid plus some ammonia here. And in this case, the H plus is going to go over, and that's going to give me NH4 plus and our Cl minus in this case, which is our ammonium chloride. If you put those guys together, that's the ammonium chloride. So again, if we think about what might be happening here, obviously here we can see that this HCl and the Cl minus are related to each other. That Cl minus comes from HCl, which is a strong acid, which means we don't have to worry about that guy going through hydrolysis. It is going to be neutral again because it comes from something that is strong. NH3 though is ammonia, and that is a weak base, which means its partner over here really is conjugate acid in this case, will actually go through hydrolysis again because it comes from a weak base, which means the NH4 plus is relatively strong enough in the sense to go through hydrolysis and react with water. So what's going to happen is you actually will have the NH4 part there of it that will react with water in a hydrolysis reaction. Once again, understanding this relationship here, that comes from a weak base, this is an acid, it should tell you exactly what it will do. The NH4 plus will act as an acid and donate the H plus over to water in this case. Once again, just like in the last one, you will then produce where it came from. So once again, it will always produce basically where that salt part came from, which is NH3, and you will get H3O plus in this case. Now, again, the production here of H3O plus should tell us several things before we even do the calculation. It should tell us we should hit an acidic pH because we are producing H3O plus in that solution. Also should tell us we should use a Ka value here when we're doing the calculation. Once again, in this problem, you would probably be given the Kb value for NH3. And again, you'll have to use that Ka times Kb equals Kw to switch around. This also would require an ice table where you would solve for x. In this case, though, x actually will equal the H3O plus or the H plus, which means you could actually go directly into the pH at that point, and you will hit a acidic pH, or should hit an acidic pH. Question on that there. Now, in addition to basically salts that come from a weak base that will go through hydrolysis and produce an acidic solution, there's actually a second way that you could get that, which is some small metals can actually do that. And a lot of transition metals that have like a +2, +3 type of charge have the ability to also become an acidic salt. So basically, if we have this guy here, which is a complex ion, later on you'll learn how to name it properly. But basically what that is you have an aluminum that has a +3 charge, and it basically has attached to it, really through the oxygen, 6 waters. And I'll just draw it like this here. 1, 2, 3, 4, 5. And we'll go 1, 2, 3, 4. We'll go one more up here. And I'll draw this one out. Looks something like that. And basically, it has basically 6 waters attached to it. They are Lewis bases. And this overall thing has a +3 charge because the water is neutral, even though there's 6 of them. And what's going to happen in this particular case is just another water floating around will basically take off one of those hydrogens off of the water that's attached to the metal. By the way, that is really what is happening when you write aqueous next to something like this. It actually is surrounded by waters, is basically what that means. And that's basically what that is. That then would produce actually H3O plus, and that is going to make this acidic. If you're kind of wondering how we get to this crazy looking formula here, it's quite simple. If we look at what just happened, we still have 1, 2, 3, 4, and 5 waters still intact. We took off a hydrogen, an H plus, from one of the waters, and we're left with an OH, which is that guy. And obviously, we still have our aluminum in the center, which is that guy. And the overall charge does change because this guy had an overall charge of +3. We lost a H plus, right? We lost an H plus, which means when we lose an H plus, we become one more negative. So instead of +3, it now becomes +2 because OH is really OH minus, right? So +3 and -1 gives you a +2 overall sort of charge. Any question on that? So a lot of transition metals, +2s, +3s, large sort of charges can basically do this, where basically one of the waters that's attached to it as a ligand a Lewis base basically will lose a hydrogen and produce H3O plus. Any questions on that there? All right, let's try one here. What is the pH of a 0.45 molar KCl solution? First thing you want to think about is this is a salt, which is KCl. You want to think about what does it really break apart into, which is K plus and Cl minus. You may also want to kind of think about maybe what acid and bases they came from, this salt. Most likely, if you had to hedge a bet there, maybe a little hydrochloric acid and a little potassium hydroxide there would get you some water and probably the salt of KCl. That means potassium, which is group 1 on the periodic table, means that it is a neutral salt, will not go through hydrolysis because it most likely came from KOH. So that's neutral. And Cl minus, as we talked about, came from HCl, which is a strong acid, which means it's going to be relatively weak and also not go through hydrolysis. So this is actually a neutral salt where the pH here should be 7 in this case. Any questions on that one there? All right, so let's take a look at one where you probably need to do a calculation. Try this one. Consider 0.3 molar sodium fluoride. What is the pH of this solution? Ka value for HF is 7.2 times 10 to the minus 4. Okay, let's take a look since we're getting to the end here. So once again, we have a salt. Which is our NaF here. And again, it's going to break apart into Na plus and F minus. So once again, we want to kind of think about, will any of these guys kind of go through hydrolysis? Bless you. Based on our past conversations, obviously sodium is group 1, which means it's neutral. We don't have to really worry about it reacting. F minus most likely came from, I would say, this guy right there, HF. And since I see a Ka value with HF, I know this is a weak acid, which means this guy's going to be relatively strong conjugate base. and it is going to go through hydrolysis. So it is going to be the F minus here that is going to go through hydrolysis. That means that it will react with water. And again, by thinking about how it's going to react, it is going to be the conjugate base, which means it's going to accept the H plus. By the way, logic also tells us it doesn't have an H to give, so it can only accept, right? So don't overlook that as well. When it does, as I mentioned before, it always produces where it came from, which is good. And in this case, it is going to produce hydroxide. So right off the bat, we should know that this guy is going to be basic, right? Because we're producing hydroxide here. We would do an ice table, and we would go 0.300, change minus x plus x plus x. That means at equilibrium 0.3 minus x, x, and x. This would go into our K value of our products, which is HF, and our OH minus divided by our F minus. And this should be a K what? Should be a KB, as we have hydroxide here. As you can see, we're not given the KB, we are given the Ka, which is very common in these type of problems. That means we do need to convert into the KB, which would be our Kw divided by the Ka value. So that's 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. That is going to get us here. We'll go 1.4, it looks like, times 10 to the minus 11. So now that we have the correct K value, we're going to go basically x squared divided by 0.3 minus x equals our KB, 1.4 times 10 to the minus 11. We're going to assume x is equal to 0. And that would get us basically x squared divided by 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply, then square root, right? So we'll go 0.3, a little square rootage. Going to get us a value here for x of, in scientific notation, 2.04 times 10 to the minus 6. We're going to divide that by 0.3 and times it by 100, and our check is good. We're nowhere near 1% at all. We do need to remember, though, that that is our hydroxide concentration. So the hydroxide concentration is essentially 2.04 times 10 to the minus 6 molar. That will get us our POH first, not our pH. And that's going to get us there 5.69. Again, to get to the pH, we could just take 14 minus that. And now we should hopefully have a basic pH of 8.31, which is basic and what we would hopefully expect in this case. Any questions on any of those steps there? So again, common errors people do on this is not being able to write the equation correctly and end up with H3O plus. I would say most common errors, people do not switch out the K value for the right K value. They just use the one that's given to them. So again, you want to make sure that you think about what's going on and not just jump in with the numbers that are given to you. Any questions on that there? All right, we're laid up there for today. We are doing equilibrium.